All right, let's get started. So just a small comment first about the exam. So I did go through basically tutorial on how to use Proctorio, which is part of Canvas, which essentially starts video on, it's a system that basically goes and starts the video while you're taking the exam. And I did actually bring up issues that some of you noted you had in different other exams, and it seems that by now there are suggested workarounds. So I think it's going to be a good system. So a system to take the exams. And now I will send an email to everyone if you haven't. So how many of you actually have Proctorio already installed? There's one person, maybe a couple more. Okay. So I'm going to send all of the instructions, the way we're going to use it. So the exam will be posted on Canvas. I think to avoid download issues, I can just basically load questions as sort of like quiz questions in Canvas, but those quiz questions will have upload. So you will basically solve the problems, and after solving them, you will scan them and upload the file. So scanning part will be the part where basically the minimum of it is just showing the solution to the video, and then scanning it with some sort of a scanner. Does everybody have some sort of a scanning solution on their phone? So far you've been doing homework, so that's basically going to be the same procedure. So I'm just going to expect you to basically scan that, send it to yourself, and upload to Canvas. And we're going to have like time allowance for that. And the way to verify things is that you show what you solved to the camera. And if there are any questions or issues like that you possibly have added to that solution or something, that can be compared. So there's a way to verify. So, and again, like there's a number of classes seem to have some issues. We're also a smaller class, so I don't expect a lot of issues, but I'll try to avoid, based on the experiences of faculty who have used Proctorio so far, I will be able to I think, avoid those. And again, we're a smaller class, so if you, for some reason, cannot upload, you can always just email me the scanned solutions, and we can figure that out with as many students as we have. That's not an issue, even if all of you just email me. But if it's uploaded to Canvas, then I can also grade. And basically, since I have a tablet and I can write and grade just like I grade normally. But then it's easier to send you graded exams back compared to scanning those on paper. Okay, so again, I'm going to send an email now that I've gone through basically training on how to use Proctorio. I'm going to send an email about both checking once again that the time on April 27th is good for you, as well as how to install Proctorio and enable it if you haven't already. Okay, so those are some of the practical matters. And now we will go back to our problem solving. So let's go back to our problems. So any questions? Issues?
Will you be online during the exam time in case there's questions that come up?
Yes.
Okay, thank you.
So at least for the portion of time I'll be available. So definitely. And I will also provide you with my, so one thing is the connectivity. or there could be an issue that could come up is, oh, your internet goes down. I mean, literally, there could be a dog in your backyard that chewed through a wire, right? And the internet goes down. In that case, you do need my phone number to let me know. And one thing that's good about Proctorio, so technically, I could let all of you just record yourself by yourself, but Proctorio actually makes note of that. So it basically monitors your connectivity, and it says, okay, it seems that the internet was on and off, but it came back, and it's gonna basically report if internet is down for like half an hour out of, right, 2 hours. So there are certain issues that software basically automatically monitors that can be then verified much easier than anything else. But that said, you will have my phone number just in case that there's an issue that comes up that is outside of being, or that you're unable to connect online for some reason. Any other questions? And if you can think of something or know of an issue, please let me know, so we can kind of prepare. By now, I think there should be enough experience out there to basically, so we can avoid all of the traps and problems. Yeah? Okay, okay. All right. So let's back to our heat transfer problems. So we've been working on heat transfer or energy transfer problems, and specifically using shell balances to solve them. And that's a standard procedure where basically my standard procedure basically looks at defining a problem, then looking at the problem geometry, trying to define a coordinate system that aligns with the solid boundaries in that problem as much as possible, or any kind of boundaries really that bound my geometry, that are boundary between different materials. And then once you figure out the coordinate system, in that coordinate system, you define a little shell, and you balance, in this case, energy transfer across the boundary of that shell. And what comes out at the end of that balance, including action outside of those boundaries. So basically, what is in this case, the work of the outside forces or any kind of sources that you might have within that shell. Then once you balance that out, you will get an equation. And ultimately, in heat transfer problems, we are looking for the equation for temperature. So even though our differential equations that we get at the very beginning when we balance using combined energy flux that we have defined for this problem, it can look really simple, but the moment you basically put all of the ingredients in, it can get complicated. So let's go to the specific problem that we've been working on. We have heat conduction, and we have our what used to be a Couette flow problem. So we have a cylinder that is moving at the constant angular velocity omega. So its linear velocity is omega times the radius r of it. And then we have a static cylinder at the inner part of the problem. So I have a laminar flow of incompressible Newtonian fluid in between these two cylinders. Now, we have solved this problem already, and we actually have the velocity distribution v theta that is a solution from our momentum transport. This is a common approach in problems with of heat transfer that actually involve fluid flow. We assume fluid part or fluid flow part essentially solved. It has been solved previously, therefore we can just use that solution here in adding essentially energy transfer to it. Now, there is actually some heat transfer because of the friction in between this is the part that we ignored previously or simply didn't look at it. So essentially, if I have different layers of fluid here moving at different velocities, there will be some friction in between them, and that friction, some of that will essentially be it will produce heat, and it might actually heat the fluid itself. This is something that in momentum transfer we simply ignore, but here we're saying, okay, there might be cases where this is important. Let's actually solve for heat transfer. So basically, we also, so this is something that happens regardless of what the temperature is that we're having the cylinders at, but here we're going to actually add to it. So we're going to say that inner cylinder is a temperature T0 and outer cylinder is a temperature TB. Those temperatures are possibly the same, or maybe they're not the same. Either way, we're going to solve the problem completely. So one simplification for this problem is to basically sort of straighten out these, assuming that this radius is very large. Okay, so I'm looking at this little box. If this radius is very large, then these lines that are curved inside this box are essentially very close to straight. And I assume that instead of having this kappa r and r radii, so basically the difference between them is r minus kappa r, I'm just assuming, I'm going to call that width b. Okay, and I'm just going to look into the straightened problem. This is akin to the fact that we're often straightening the Earth, even though Earth is a sphere. We're assuming this very large curvature. So as far as our experience is on the Earth, it's in our local coordinate systems relatively flat. Now, basically, we're going to straighten that out, and then we're going to have a small Cartesian coordinate system. And here it is, my straightened in green. It's the difference between these is b. And I'm going to align x direction to show upwards, to point upwards, z direction to basically move in this, what used to be theta direction, but is now straightened out. And I'm going to also simplify my life but by linearizing this velocity profile inside of this flattened part. If it's small, then linear solution and that nonlinear that I showed are pretty close. And I'm just going to say, okay, this is Vz of x. This one, this velocity is 0. This is some maximum velocity that I'm going to call Vb, which is actually omega r. So basically, my linearized velocity profile is given as Vz of x is equal to Vb, this maximum velocity, x over b. And my b goes from, well, my x goes from 0 to b. Okay, so I know my velocity profile. And now I'm going to do the shell balance. My combined energy flux is given as this, if you remember, comes from rho internal energy. It's just that the pressure part from the molecular forces has jumped in here, and this is now enthalpy instead of just internal energy. So basically, I have this energy part that is basically convective part of energy coming in with the fluid moving at velocity v. Then I have the work of what's left here is the work of shear forces and viscous forces, which is essentially my shear stress applied to velocity. And I have my heat transfer as per Fourier's law, that is the component part that is just there because of the differences in temperature. Okay, so in this coordinate system, my energy flux vector has two components, Ex and Ez. And when I look at the little shell and balance it, so basically I look at what comes in through all of the boundaries as well as coming out. So this is in and out in Z direction, Ez. So this is this part. And then I have in and out in X direction. I sum all of those up. There's a plus here missing. And when I sum them all up, since I don't have any generation within the volume and we are ignoring work of any kind of gravity forces, this is too small to look at that. And I don't have any production term inside this, this is equal to 0. Okay? So when I basically divide by the volume of this shell, I'm going to get first term and second term here, which when I take the limit as delta x and delta z, I'm going to start writing in slightly fixing my typos from last time. This should be, oh, Okay. Delta delta Z, and this should be a plus here. Okay. Just a moment. Okay. So as I take this limit, I get a partial differential equation, the derivative with respect to x of Ex plus derivative with respect to Z of Ez is equal to 0. This looks pretty simple, doesn't it? Now let's actually look at, luckily, well, it's going to look even simpler until it looks a little more complicated. So first we're going to look at this Ez part, because that one is actually going to turn out to be 0. So if I look at what my Ez is, and I'm going to change my color to blue. So I'm looking at this term first. So my Ez component of my energy flux vector is to 1/2 rho kinetic energy plus enthalpy plus the time, the component that enters through Z side, enters and exits as necessary, plus the Z component of the work of the viscous forces, plus the component of my flux Q. Now my VZ, so I'm looking at dBz of this. So if I look at this, if I take the derivative with respect to Z, this is going to be 0 simply because VZ is a function of X. It's not a function of Z. Now, what do I actually have? What is this? I mentioned that when we actually do these, this is a tensor. Tau is a tensor, right? I tend to omit these. So this is really a matrix times a vector, really. And luckily for the Cartesian coordinate system, you have actually what is this expression on the inside cover of BSL. Let me just quickly. Do you see me showing it? So there is my BSL is falling apart, but there is actually the inside cover of BSL. The first page actually has the expression for X, Y, Z components of this. Did everybody see it? So per inside cover of BSL, and this will be reminiscent of multiplying matrix and a vector. This is actually tau Zx Vx plus tau Zy Vy plus tau Zz Vz. Okay, so inside cover of BSL. Okay. So what is that? Do I have Vx? What is my Vx? Anybody awake? I really don't have this term at all because I have a simple coordinate system with in 2D. Vx is 0, right? Tau Zz is minus mu 2 mu dVz dz. And that part, that's 0 too, because my Vz is just a function of X. So luckily, this term is a 0 as well. And then I don't have a temperature difference in Z direction. My temperature difference is in X direction. So there will be, if there's no temperature difference or gradient in temperature, this is going to be equal to 0 as well, because there is no dt dz. It's equal to 0. There's no temperature difference in Z. Okay. All right. So luckily, it turns out that the ZD Z is equal to 0. Excellent. So what I'm really left with is an equation. Dx is equal to 0. Okay, so now what is Ex? Very similar equation applies as the one I wrote up there. It's just now in X direction. So I have rho V squared plus rho H Vx this time, plus tau dot V X component plus Qx. Now Vx is 0, so this disappears. And then this is very similarly on the inside cover of BSL, so I can find that it's tau xx Vx plus tau xy Vy plus tau xz Vz. And I'm going to write down what Qx is. It's minus k dt dx. Again, I have only the dependence on x, so I'm going to now use regular d for it. Vx is 0, this terms disappear. Vy is 0, this term disappears. What is tau xz? If you have a pet, even your pet should know by now that tau xz is equal to. Apparently your pet doesn't know. Anyone? This is Cartesian coordinate system. Vz is a function of x only. What is tau xz? Nobody's listening. Adrian, are you there?
Yes.
What is tau xz in a simple parallel plate Cartesian coordinate system like this one? Laminar flow of a Newtonian fluid. Shear stress. So Vz is a Vz of x, right? I have parallel plates, go from 0, right? This is Z, this is x. It's minus mu. What do I do to Vz? Derivative? Anybody? dVz dx. Does everybody agree? Tau xz is minus mu dVz dx? Yes? Okay, that sounds familiar, I hope. Okay, all right. So this is times Vz minus k dt dx. I know my Vz. Vz, I know Vz. We took a very simple function Vz of x and approximated it as Vb divided by b times x. Okay, so for x is equal to 0, I get a 0. For x is equal to v, I get a Vb, which was my maximum velocity on that on the outside. Okay, excellent. So what is my dVz dx then? It is really Vb over b. So when I plug that in, dx, it is d dx of all of these terms here, and I have Vb over b as a derivative of Vz with respect to x. So it's minus mu Vb over b and then times Vz, which is Vb over Bx, minus K dt dx. Okay, so when I look at that, that means if derivative of this term inside the brackets is equal to 0, that means that that term is equal to constant. And I know how to solve that. So basically minus Vb over B squared x minus dt x has to be equal to constant, and this is the first constant I'm encountering, so I'm going to call it C1. When I put all of the appropriate terms, I'm going to isolate dt dx on my left-hand side, and everything else on the other side. So for that, I had to divide by minus k. So I'm going to have minus mu over k, v over b squared x minus c1 over k. And I integrate that once again and get minus mu over k, v over b squared x squared over 2 minus c1 over k x and plus c2. So now I have two constants. I have two boundary conditions. What are my boundary conditions for temperature? One is at 0, one is at B. So I have T0 on the bottom, x is equal to 0, and I have TB on the top. Yes? Okay. And so I can solve that. This is not a problem to solve. I'm not going to work out here by hand the rule, the C1 and C2, but I'm just going to write down what the solution is. So the solution is if my T0 is not equal to TB, then the solution can be, and this is the normalized form preferred. It's actually good to look at the normalized form because then I can compare different problems. In such problems, we often submit the TB minus T0 is the difference of the temperature that is driving, as per Fourier's law, the heat transfer. So that's something that that is good to normalize by. And then there's so my temperature minus T0, which is presumably smaller of the temperature, divided by the difference between them. That's called a normalized temperature. That's T0. I know all of these numbers. X over B, so I normalize my x, so x is between 0 and 1, times 1 minus x over B, plus x over B. And if my, let me choose the color, how about this green one? T0 is equal to TB, then the same solution is T of x minus T0. Of course, if they're equal, I cannot divide by their difference. So this is the case where I'm going to look at only the effect of the viscous heating because of the friction between the layers. There is no other temperature difference that is driving the heat transfer. In that case, my solution is mu Vb squared divided by K T0 x over B 1 minus x over B plus x over B. Okay. This number here is often called Brinkman number. And is equal to the rate of viscous dissipation Basically, that's the top term is the rate of viscous dissipation, energy dissipation, of course, divided by the rate of heat conduction. So what I'd like you as your quiz for today, and I'm going to open up a quiz for today, is simply to plot these distributions. So this is going to be assignment much more than a quiz. In your favorite software, it might be Python, it might be MATLAB, plot these two distributions. And I'm going to call them 1 and 2. 1 and 2. Okay. And you're going to use actual numbers just to simply have from problem use for 1, use numbers from problem 10A3. And 10A3 has only T0, it doesn't have TB, so you're going to use and TB is 178. And for 2, just use this. For the problem 10A3 is really this case 2. To use 10A3. And what I want you is also compare these distributions for T of X. So I want to plot these two distributions. So T of X versus X, or even X divided by B, however you'd like to plot it, and see what the difference is between that and simply a linear case. So what is the difference? Linear solution. Is it clear what I'm asking? So again, just to get a feel for a specific problem so that this is not just some sort of abstract solution to a problem. So one thing in this type of problem, so this is often important in lubrication theory, and this 10A3 is a case of a lubricant. Often actually in Couette flow and viscosimeters, one might need to take it into account, because if this viscous heating term is high, then in those cases, we actually might need to adjust the viscosity. What is viscosity? And this assumption of viscosity mu being independent of temperature might actually fail. So that's something that we need to understand. Often, well, you're going to solve this problem 10A3 for lubricant, assuming lubricant is Newtonian fluid. That's not necessarily the case. What would I do differently if I actually had a non-Newtonian fluid? What would actually change in solving this problem? Any idea?
The shear stress. What you plugged in for the shear stress would change.
Right. So I would actually have, and this assumption solution for velocity, right? So I assume that my VZ of X is some given function, and here I actually just linearized it, right? Well, that solution would be something different. And in this particular case, I could actually take, so we solved parallel plate problem for a lot of different fluids, right? So you could basically just take the appropriate VZ and what you plug in. Of course, that then complicates ever so slightly how you're going to integrate this. But technically, well, depends on the problem, right? We have here, we would have like dt dx that we're trying to solve. Where is that? Right here, right? So I'm expressing dt dx, And it's this term that would be, that has the, this would be much more complicated term depending on what that velocity distribution looks like for the non-Newtonian fluid you're looking at. But again, the basic assumption is that you've already solved, and we have solved many problems, and that you have this velocity distribution. So you're just basically plugging things in. A lot of these, the way you're solving the problem stays in place regardless of the Newtonian versus non-Newtonian assumption. It's just that it might get a little more hairy to integrate. Any questions?
Can you explain what the assignment is again? I was
So
kind of confused.
assignment is just like, so here's this formula 1 and formula 2 is the solution. But this, with these general numbers, B, T0, TB, K, mu, right? And that gives you the temperature distribution for this type of problem, assuming you have all of these numbers. So 10A3 problem in BSL gives you those numbers for a specific problem. It looks at a lubricant in between. Yeah. So I want you to use the numbers provided for viscosity, thermal conductivity, and temperatures in that problem, and simply plot. These are functions. The first one, well, both are basically quadratic functions in terms of x. Yes? And I want you to plot them. They're quadratic temperatures in terms of x. Otherwise, if I didn't solve this, and I just assumed, oh, I have a T0 and TB on our ends, I could just then look at the temperature distribution as linearly going from T0 to TB. So my simplest solution, 0th order, if you will, first order solution, is just a linear function that goes from T0 to TB for my temperature distribution. Yes? And if there is no temperature difference, T0 is equal to TB, then that's just a constant. I'm just assuming constant temperature everywhere. But these two formulas will give me the difference from that. The reality is a little more complex. So there's a parabolic temperature profile, and I want you to compare that temperature profile. So I think the T0 in that problem, let me quickly look it up. I think, yes, it's this T0 is 158. That's what, and that's an assumption. And you're gonna get that the maximum temperature within this is something different from that. Maybe it's 170 or something like that, right? And when you look at it, well, it's different from 158. Does that difference matter? Depends on the problem. And is it going to change the viscosity or any kind of other properties of the problem you're solving? Yes?
And we're comparing this to the parallel plates model for the linear solution. Is that what you said?
All I'm just gonna say is plot. So basically there will be, this is your x, this is your t of x, right? So there's the simplest case is T0, TB, and you're going from, and this is your 0B, right? You're going, this is linear, right? That's what I want you to compare against. Your solution will go something like that.
Okay, thank you.
Yes? So it's some sort of parabolic function versus linear. What is this? So there's a difference here, right? And the maximum difference could be, I don't know, 20 Fahrenheit, 30 Fahrenheit, depending on the problem. So I want you to get the feel for that difference, because again, this is the simplest assumption, is just assume linear thing in between. That's basically if there was no fluid in between. Yeah? Or the fluid was static rather. So fluid moving, this is the difference. So I want you to get so that these are just not formulas, abstract formulas, that they actually have numbers associated with it. And again, depending on the problem, these 20 Fahrenheit degrees might or might not be cause any issues. Okay. Another thing that I'd like to briefly comment, and that's basically going to wrap up our session for today, is heating. So there's a term that we actually look at for this. Viscous heating, SV, is mu for this problem is V squared over V squared. It's called viscous heat. Or that this term simply quantifies viscous heat. And the way it's actually derived is by looking at the work. So this is my parallel plate. We have a shear force, right? Acting here. So there is the top plate, or this cylinder here. We assume that it's plate because we straightened it. That cylinder is moving, and because of that, it's exerting work on the fluid below. So that work, oops. If you remember, it's F dot V. So in this case, it's basically going to be, since my plate is on the top, it's basically minus tau xz times the area. So shear stress times the area times VB. The velocity on the top plate is VB. And then I divide it by volume. So I can actually see how much heating per volume does this moving plate cause inside of the fluid. And my volume is WLB. And when you actually plug in what for this problem is tau xz, you're actually going to get precisely mu v squared divided by v squared. So this is a way to look at it in an integrated way, just like what is the work of the top plate exacted on the volume of fluid that we're looking at. Questions? All right. So after this, we're gonna, I think, yeah, we're gonna solve one more problem next time, and then we're gonna briefly mention what happens when I have a time-dependent change and what are the formulas that we use.